Hi, everyone, and thank you for inviting me for this meeting, and thank you all that are attending. And I hope I can explain a bit about, or explain what this work is, and maybe answer some questions you might have. As TC just said, we have this paper published recently where we provided Earth Engine code to derive LST from the Landsat series. So I have a PhD in geophysical sciences with applications to remote sensing, and my PhD was pretty much on land surface temperature retrieval from satellites. And that's what I've been working on since then within the Landsat, which is part of the EUMETSAT. So it's the European Agency for Meteorological Satellites. So I have a large experience with land surface temperature estimation. And I want to start, wait, not moving. Okay. So I want to start this presentation by explaining why we did this work. So we are a European agency, so we really don't have to process satellites that are not European, but I had this student doing a master thesis on the urban heat island effect in Coimbra, which is a Portuguese city in the center of the country, more or less, close to the ocean. And as you know, to study the urban heat island effects, it's desirable to use a satellite that has high spatial resolution. And so we decided to use the Landsat. Now, she was, her master degree was on geology, and she didn't have much experience programming. They don't have many courses with programming at her course at her university, so I thought it would be interesting for her to use the Google Earth Engine. And then there weren't that many Landsat LST datasets over Portugal available, so what I proposed was that we would work on deriving our own LST for Landsat, and then she could use it to do her study on the urban heat island effect. And as I said, because she didn't have much experience programming, I thought it would be easier for her to learn how to use the Google Earth Engine instead of learning Python and then having to process all the data, which can be quite complicated, and the GE simplifies a lot of the processing. So even though she had to learn a bit of programming, I did a lot of parts of the module, so she had to learn a bit to use it and everything, but thought it would be easier. So she helped me with the algorithm development and calibration, and then we set up everything to run on the Google Earth Engine. And the good thing was that from there, she didn't really need to have many resources to work on her project. And she could do the full analysis of these large volumes of data directly in the Earth Engine, wherever she was with her laptop. And she was pretty much very independent in working with the data. So I think this is a benefit of using the Earth Engine, especially for students that don't have usually access to a lot of resources to process the data. And so we started setting up a production chain for what we call a production chain for the Landsat land surface temperature. The algorithm we decided to use was the statistical mono window algorithm. So this algorithm only requires one infrared channel, which is what is available on the Landsat. And this was developed by the ClimateSat for the older generation of satellites that also only had one channel. And this is a very simple algorithm. It's simple linear regression. that depends on the brightness temperature of the infrared channel, and then requires an estimate of surface emissivity. And the tricky part of using the algorithm, the thing that, so this is very easy to apply, but the thing that usually users don't easily have access to is the algorithm coefficients. And to have a robust calibration database that represents all possible situations when the satellite is retrieving LST, that is the tricky part. And this is something I work with her, and we use the radiative transfer model to simulate several atmospheric and surface conditions and what the satellite would measure, and then calibrated the algorithm with this data. And for this algorithm in particular, what we do is we separate or we break apart situations depending on the content of water vapor in the atmosphere, which is the main atmospheric component that interferes with the signal in the infrared. And to account for their interference, what we do is, instead of having explicit dependence, we just break apart situations where you have different water vapor contents and calibrate the coefficients for each sort of bin of water vapor in the atmosphere. And this is the calibration residuals for each Landsat. And as you can see, the algorithm works reasonably well. Obviously, as you go towards the very high water vapor contents, you start to have larger areas because of the interference of the water vapor in the signal. But this is just something that we really can't do much about, especially when you only have one channel. So when you have two channels, you can work with the difference between the two channels to try to improve or to try to solve this problem in the signal, or this limitation of the signal. But when you have only one channel, it's natural to have higher errors as you go towards higher concentrations of water vapor. So if you want to access the code and look at it as I'm going through it, these are the links. So there's the up one is directly for the Google Earth Engine repository, and afterwards, after the paper, I also created a GitHub repository. So because there were some people having trouble accessing the Google Earth Engine one for some reason, so I just decided to create a GitHub one. That's the reason why it's not. So this link is not in the paper, but if you want to use it, you can also use it. The code is up to date with the one in the Earth Engine. And I'd like to start by saying this because I've had so many people asking me, contacting me, asking me this. So when you click the link, this is what will show up in your window. And the script area will be blank because this is a link to a repository, not scripts. So this script section will be blank, but the repository will show up in your scripts tab. So although it looks like the link is not working, so I had a lot of people contacting me asking why the link was not working, if I could provide a new one. The link is working, it just, the code will show up in your scripts tab. So I just decided to add this here because it seems like it's a thing that happens to a lot of people. And I don't know, maybe somebody with the same question might see this video, and this is where the code will be. So now going through the structure of the code. So there are several phases of data processing before you can compute the land surface temperature. And there is a main script, which you could call a wrapper. So this is something you usually use in computer science. And it basically loads all the modules and defines all the links, the paths to the data, everything that is necessary for the code to run. So it will load all the image collection that it's necessary based on the user selection. So if the user will tell the code which Landsat and what is the date range they want to process and where do they want to process. And this code will load all the data and call all the necessary modules to compute the land surface temperature, and then returns that data set. So now I'm going to go through the rest of the code. So the first phase is to characterize the surface, because we need to know what is the surface conditions to estimate or to have a better estimate of the emissivity. And to do that, we use the NDVI. So this is the normalized vegetation index. I'm not sure if all of you are familiar with this. So this is simply an index that is used to establish how green vegetation is. And in this case, because emissivity is very sensitive to contrasts between the vegetation and non-vegetated areas. So vegetation usually has very high emissivity values, and bare soil can have much, much lower values. So typically, to estimate emissivity, we just use a weighted average between what's green and what it's not green, and take the emissivities of those two components, and we can get a pretty good estimate of the emissivity at a pixel scale based on the subscale information that we have on the vegetation fraction. And to do that, we will need to load the surface reflectance data. So to compute the NDVI, somebody has their mic on. So to compute the NDVI, you need to have surface reflectance data. You cannot use the top of the atmosphere values because it will have, atmospheric interference. So the first step, obviously, is to mask any clouds because we cannot get any signal under the clouds. And then the NDVI is a very simple computation. It's just the normalized difference between the near infrared and the red channels. And then we convert those NDVI values into a fraction of vegetation. And why we do that is because, so the NDVI is very useful, but it will be for when you have very low values of vegetation, it will quite be sensitive to what's is on the soil, what type of soil, what type of surface, if it's water, if it's not. And in this case, we don't really want that information. We just want to know how much vegetation is in the pixels. So we set up a minimum NDVI value for which we assume anything below that value will simply be bare. So there's bare in terms of vegetation. So there is no vegetation below a certain value, which we take from the literature to be 0.2. And on the other extreme, NDVI values tend to saturate as you go towards very high values of vegetation. So what we do is we set up a value of NDVI from which any value above, it's just very dense vegetation anyway. So, and that value we also take from the literature to be 0.86. So basically we go from having NDVI having a value between 0 and 1, which will be an indication of the fraction of vegetation inside the pixel. So the next phase of the code is to then, since we already know how much vegetation we have for that a given observation, is to compute the emissivity for that observation. And to do that, so as I said, the emissivity of vegetation is quite stable. It's very high and usually quite stable, so it doesn't vary much with vegetation type. There are slight variations, but it's much lower than the variations we see for bare ground surfaces. And to get a good estimate of those bare ground emissivities, it's the tricky part. So what we do is we use this database from Aster that uses the direct retrieval of emissivity. So the algorithm that is used separates the emissivity temperature signals and gives you a direct estimate of the emissivity of the surface. The problem is, and it's also a very high resolution data set, the problem is that the aster has very low a very low number of overpasses over a given period of time. So to get a full global coverage, what the authors of this data set did was they average all the observations for several years. So what you have is sort of a climatology of emissivity over the globe. And they also provide the respective climatology of NDVI. So your emissivity is a static emissivity. And in places where you have a lot of vegetation variability, like a seasonal cycle, or even from one year to the other, you can have significant changes in emissivity. The emissivity might not be well represented. So that's where our fraction of vegetation that we just computed goes in. So how do I combine these two data sets? So as you remember, I said before that we compute emissivity simply assuming that there's vegetation and there's something that it's not vegetation. We call it bare ground. And the emissivity of the pixel will be a sum, and weighted average, let's just say it, of the vegetated component and the bare ground component. And the weight is simply the fraction of vegetation. So the vegetated part, as I said, is pretty stable, takes very high values, so we can just assume typical value from the literature. And then the bare part is what we'll be getting from the aster. And to do that, we simply invert this equation. So we have the emissivity estimate. We can compute the fraction of vegetation from the aster NDVI that is provided, and taking a value of vegetated emissivity of 0.99, we invert and can get the bare ground emissivity. Now, afterwards, this bare ground emissivity will be used in another module, combined with the fraction of vegetation that we computed from the Landsat. So it's the actual vegetated fraction of vegetation of that at that time. And we just apply the same equation, also using emissivity for vegetation of 0.99. So here, there are several values. If you work with this type of data, there's a lot of values showing up in the literature. I did extensive research on this and found that it seems that because this is very high resolution data, the best estimate or the best value to use would be a very, very high value. So 0.99, some other papers use 0.98. But it actually seems from our quality assessment that using 0.99 works better. But if you find that it's not taking, or you don't have good enough values over the area you're studying, this is something you can always change in the code, obviously. One of the benefits of having the code fully available on the Google Earth Engine, is that you can change anything that you need for your application. So this is just to show you the importance of doing all this NDVI correction, I would say. So this is the aster fraction of vegetation we computed from the NDVI and the respective band 14 emissivity, which is the band that it's closer to the Landsat infrared band. And you can see here the difference. So this is a climatology, and then the Landsat image I'm showing here is around May, which is springtime here in Portugal, and you're starting to have a lot of very, very green vegetation around this time. So you can see the difference between having the two data sets here. You have much greener areas, sort of, and that translate into much higher emissivity values when you compute the emissivity. So this will have a large impact on the LST estimation. Finally, the last phase of the, almost, I would say, close, I don't know how you say it. So it's not really the last, but almost at the end now. So an important step as well, because as I said, the algorithm takes into account the water vapor content of the atmosphere. So we need to get that information. And the way we do that, we get the water vapor estimates from a reanalysis, from the NOAA reanalysis. And because, so this data is 6 hourly, so the way we do to get the actual or a better estimate of the water vapor at the time of observation of the Landsat, because in 6 hours you can have significant variations of water vapor. Usually they are not very large, but in some cases when you have fast moving systems and things like this, you can have significant changes in water vapor within 6 hours. So what we do is we take, so this code seems very complicated, but it's basically here we just select the dates we want to use to filter, to set up our date range to load the reanalysis data. And then for each one of those estimates, which are every 6 hours, this will be 2 full days, we compute the time distance to the Landsat observation time. And then we select the 2 closest ones, which in the end will be simply the one right before and right after the Landsat observation time. And then this is simply so we select those 2, take the water vapor, take the time difference, and do sort of an average. So this is simply a linear interpolation between the time before and the time after to get the best estimate of water vapor at the observation time of the Landsat. Then, because the algorithm does not require the water vapor explicitly, what we need is to convert that into the beams that I used to calibrate the coefficients. So we use beams with steps of 6 centimeters for the water vapor. So this is just the way we convert the water vapor values into beams. And then we just add that information to the image collection. So now the final part, the final module, we compute the LST. So we have the water vapor beams already available, and we use that to map the coefficients into the image. I'm not showing here there's a module with all the coefficients available. I'm not showing here because it's a lot of code and there's not really much information, but if you want to see it, you can access the repository and just check it. And what we do, we map the coefficients, and then we just apply the algorithm I just showed you. So A, B, and C, and there's the emissivity we computed and the brightness temperature from the satellite. And this is the example that's in the paper. You have here the brightness temperature of Landsat and the respective land surface temperature. You can see high differences between the two due to the atmospheric effect on the data. So I wanted to sort of wrap up this talk by showing you just the quality assessment we did. So we were careful to evaluate how good our LST estimates were, and to do that we compared with several in situ stations that are typically used to validate land surface temperature for several products available, mobilities, etc. So these are all the stations that we used. Results are pretty good, so we're very confident on the quality of the product. And then if you want, or if you have a station or you want to check the code that we used to extract the time series that were then compared with the in situ data or the station data, it's fully available on the repository. It's the example 2 code. And you can see here, it makes this nice time series of the whole Landsat series. And on the bottom of the script, there's a little bit of code that is commented that you can use to extract the data if you need. And there's also another example file in the repository that shows you how you can use the code to generate, to process, or to compute the LST for one given image, and then show plotted in the map together with a bunch of other variables available. Then there's also some code available that shows you how you can extract the images, which is what I used to make all those images that I showed you before and the ones that are in the paper. I processed them with another software afterwards, so they could have all the scales and the color bars and everything. Unfortunately, to my knowledge, Earth Engine, or at least when I did this paper, the Earth Engine didn't allow us to make pretty pictures, let's say it like this. As you know, when you're publishing a paper, you need to be careful. You need to put all the geographical referencing in the image and the color bars, and it's not easy to do this in Earth Engine for now. So I hope this will change soon. So what I did, I extracted a GeoTIFF and then uploaded it to a different software to get the images. But I think with the examples, you can easily see how you can use the code for your applications in case you need it. And that ends my talk. Thank you all again for attending. And if you have any questions, I hope I can help.